Hello students, welcome to the lecture on solid state, and after this lecture we will be able to learn the following objectives: classification of solid based on different binding forces, defining crystalline state, understanding crystal structure and lattices and unit cells. Let me first tell you what solid state means. There are three states of matter: solid, liquids and gas. Solid possess the most structural diversity, whereas gases and liquids consist of discrete molecules that are randomly distributed due to thermal motion. Solid consists of molecules, atoms or ions that are statistically positioned. Crystal structures are usually determined by the technique of X-ray crystallography. This technique relies on the fact that the distances between atoms in crystals are of the same order of the magnitude as the wavelength of X-rays of the order of 1 atom or 100 pm. A crystal does act as a three-dimensional diffraction grating to a beam of X-rays. The resulting diffraction pattern can be interpreted to give the internal position of the atoms in the crystal very precisely, thus defining interatomic distances and angles. From here we get the definition of solid. A solid is defined as that form of matter which possesses rigidity and due to which possesses a definite volume and a definite shape. The solids can be classified into amorphous solids, crystalline solids. The solids which do not have any definite shape geometrically are called amorphous solid. These solids are also called supercool liquids and are without sharp melting points. That is, these have short range order of their constituent atoms like that in the liquids. Example: glass, rubber, plastic, etc. Amorphous solids are isotropic, that is, their physical properties are same in all directions. Actually, here the particles are randomly arranged and disordered due to which all directions are equivalent, hence all the properties remain the same in all directions. A crystal is a solid which is composed of atoms arranged in an orderly repetitive array, that is, a homogeneous anisotropic substance having a definite geometrical shape with surfaces that are usually plane with sharp edges. In many solids, we may not clearly see the shape of crystal because several small or micro-sized crystals are tightly packed together without any specific order. Such a substance, which is in fact crystalline but is superfine to be seen as crystal, is called microcrystalline or polycrystalline solid. Example: many metals and alloys. A copper wire has microcrystalline structure. Classification of solids based on different binding forces. Every amorphous and crystalline solid possesses certain types of inter- and intramolecular interaction between its subunits that govern its overall properties. A. Ionic solids. These solids are characterized by cationic and anionic species that are associated through electrostatic interaction. All predominantly ionic salts possess crystalline structures as exhibited by common group 1 to 17 or 2 to 17 binary salts such as NaCl and CaCl2. The melting points of these solids are extremely high, as very strong electrostatic attraction between counter ions must be overcome. In the determination of the lattice energy U, the sizes and charges of the ions are most important. Ionic solids are only soluble in extremely polar solvent due to dipole interaction between component ions and the solvent. Since the lattice energy of the crystal must be overcome in this process, the solvation of the ions represents a significant exothermic process that is the driving force for this to occur. There is often a degree of covalency in the bonding. In particular, Fajon's rules describe the degree of covalency as being related to the charge density of the cation and the polarizability of the anion. In general, polarizability increases down a periodic group due to lower electronegativities and valence electrons being housed in more diffuse orbitals, thus experiencing a much less effective nuclear charge. B. Metallic solids. Metallic solids are characterized by physical properties such as high thermal and electrical conductivities, malleability and ductility. The close chemical association among neighboring metal atoms in the solid gives rise to physical properties. The non-directional bonding in metals allows for two modes of deformation to occur when a metal is bent. Chemically, metals tend to have low ionization energies that often result in metals being easily oxidized by the surrounding environmental condition. This explains why metals are found in nature as complex geological formation of oxide, sulfates, silicates, aluminates, etc. It should be noted that metals or alloys may also exist as liquids. Mercury represents the only example of a pure metal that exists as a liquid at STP. The liquid state of Hg is a consequence of the electronic configuration of its individual atoms. The most simplistic model for the bonding in metallic solid is best described via the free electron model. Since the delocalization of electrons occurs more readily for valence electrons further from the nucleus, metallic character increases going down a group of the periodic table. Although metals are mostly characterized by crystalline structure, amorphous alloys may also be produced, known as metallic glasses. These materials combine properties of both plastic and metals and are currently used within electric transformers, armor-piercing projectiles, and even sports equipment. The media has recently been focused on this latter application for golf clubs, tennis rackets, and baseball bats. Unlike window glass, metallic glass is not brittle. Many traditional metals are relatively easy to deform or bend permanently out of shape because their crystal lattices are riddled with defects. A metallic glass, in contrast, will spring back to its original shape much more readily. C. Covalent network solids. These solids are characterized by very strong directional covalent bonds between their constituent atoms. This bonding area generally leads to high melting points and bulk hardness. Due to the arrangement of the atoms comprising these solids, a variety of physical properties may be observed, as evidenced by the very different properties exhibited by the three allotropes, that is, discrete structural forms of carbon. It should be noted that although the discrete units of the extended solids are covalently bound, there may also be layers that are held together by weaker intermolecular forces such as van der Waals interaction. D. Molecular solids. This class of solid feature discrete molecules that are held together by rather weak intermolecular forces such as dipole, London, dispersion, and hydrogen bonding. Since these forces are much weaker than ionic or metallic bonding interaction, molecular solids are usually characterized by low melting points. Molecular solids may exhibit either crystalline or amorphous structures depending on the complexity of the individual molecules comprising the bulk material. As with all solids, the more complex the subunits are, the harder it is for them to organize themselves in a repeatable fashion, resulting in an amorphous structure. Unlike purely ionic solids, molecular compounds may be soluble in either non-polar or polar solvents as long as the solvent polarity between solid and solvent is matched. Relative intensity of dipole forces may be represented by the equations shown on the screen. The relative strength of London dispersion forces is described by this equation. The strength of association may be represented by the equation as shown on the screen. The potential energy between pairs of non-bonded neutral atoms or molecules as a function of internuclear or intermolecular separation may be described as a combination of attraction and repulsion terms referred to as the Lennard-Jones potential is given by this equation. For two polar molecules, the long-range electrostatic interaction between molecule dipoles must be accounted for. Hence, another term referred to as the Stockmayer potential must be added to equation 5. The D term in equation 6 is the polarity correction term based on the magnitude and direction of the polar dipoles. Single crystal comprise an infinite array of ions, atoms, or molecules known as a crystal lattice. The strength of the interaction between the species comprising the crystal is known as the lattice energy and is dependent on the nature and degree of interactions between adjacent species. For example, the extremely high melting points of salt are directly associated with the strength of the ionic bonds between adjacent ions. For molecular species, it is the degree of intermolecular interaction such as van der Waals and hydrogen bonding forces that controls the lattice energy. Ionic and covalent crystal have similar lattice energies followed by metallic bonding. By contrast, molecular crystal such as solid carbon dioxide are much more readily broken apart, a consequence of the weak van der Waals interactions consisting between the discrete molecules that comprise the lattice. The overall shape or form of a crystal is known as a morphology. Often there is more than one crystalline form of the same substance. Each form is known as a polymorph, differing in both the arrangement of constituent as well as unit cell dimensions. Most often, the energy for the inner conversion between polymorphs is small, resulting in phase changes that occur after only moderate changes in temperature or pressure. If the solid is an element, polymorphs are known as allotropes. The relative thermodynamic stability of a particular allotrope is governed by the structure with the lowest overall free energy. If the chemical contents of a polymorph are different than other forms, it is designated as a pseudo-polymorph. This often occurs due to the presence of differing amounts of solvent which will alter physical properties of the crystal, such as melting points and solubilities. Polymorphism and pseudo-polymorphism may be observed when different experimental conditions are used for synthesis. Let us now discuss some crystal structure. A perfect crystal is considered to be constructed by a space lattice, that is by infinite regular repetition in space of identical structure units. Thus, the ideal crystal is invariant under translation in steps of lattice, constant and related distances. It is also invariant under rotation in steps of well-defined angles. There are 230 basic different repetitive patterns. Crystal structures may be conveniently specified by describing the arrangement within the solid of a small representative group of atoms or molecules called the unit cells. By multiplying identical unit cells in three directions, the location of all the particles in the crystal is determined. In nature, 14 different types of crystal structures or lattices are found. The simplest crystalline unit cell to picture is a cubic, where the atoms are lined up in a square 3D grid. The unit cell is simply a box with an atom at each corner. Simple cubic crystals are relatively rare, mostly because they tend to easily distort. However, many crystals form body-centered cubic BCC or face-centered cubic FCC structure, which are cubic with either an extra atom centered in the cube or centered in each face of the cube. Most metals form BCC, FCC or hexagonal closed-packed HCP structure. However, the structure can change depending on temperature.
The simple cubic lattice is the simplest lattice structure and consists of 8 atoms at the 8 corners of a cube. In the ball and stick model shown here, the distances between the atoms are greatly exaggerated. In actuality, the atoms are packed much more closely together and touch somewhere in the structure. A more realistic model of this structure is the space-filling model. Here the size of the atoms is in correct proportion to the cell. This space-filling model demonstrates that in the case of the simple cubic lattice, the atoms touch along the edge of the cell. In the model shown here, each atom touches 3 others along the 3 edges of the cell. We can generate the unit cell of the simple cubic lattice by including only those portions of the atoms that appear inside the cell boundaries. In the case of the simple cubic cell, each atom lies 1/8 inside the cell. Since there are 8 of these fractional atoms, there is the equivalent of 1 atom inside the unit cell. The body-centered cubic lattice contains the same 8 vertex atoms as the simple cubic lattice, but with 1 body atom in the center of the cell. This simple change results in a structure that is completely different from the simple cubic lattice. Due to the atom at the center of the cell, the vertex atoms no longer touch along an edge of the cell in the space-filling model. Instead, each of the vertex atoms touches the center atom. The atoms are said to touch along the cube diagonal of the cell, which connects opposite corners of the cube. The unit cell for the body-centered cubic cell is shown here. In addition to the 8 vertex atoms, this cell contains one body atom that lies entirely inside the cell. This gives the equivalent of 2 atoms inside the cell.
The stable room temperature crystal structure for several elemental metals, a nanometer Nm equals 10 to 9 meter or 10 angstrom units, is shown in the picture. Structures of some important compounds, cesium chloride. In the cesium chloride CsCl structure, the space lattice is simple cubic. There are 2 such simple cubic lattices which are separated by one half of the body diagonal of the unit code. One lattice is occupied by Cs atoms, the other by Cl atom. Each atom has 8 nearest neighbors of the opposite kind and is bound to these 8 atoms, which are arranged at the corners of the surrounding hexahedron cube. The bonding is typically ionic. Natrium chloride. In the natrium chloride NaCl structure, the space lattice is face-centered cubic FCC. There are 2 such FCC lattices which are separated by one half of the body diagonal of the unit cube. One lattice is occupied by Na atoms, the other by Cl atoms. Each atom has 6 nearest neighbors of the opposite kind and is bound to these 6 atoms, which are arranged at the corners of the surrounding octahedron. The bonding is typically ionic. Zinc blend. In the zinc blend ZNS structure, the space lattice is face-centered cubic FCC. There are 2 such FCC lattices which are separated by 1/4 of the body diagonal of the unit cube. One lattice is occupied by Zn atoms, the other by S atoms. Each atom has 4 nearest neighbors of the opposite kind and is bound to these 4 atoms, which are arranged at the corners of the surrounding tetrahedron. The bonding is typically covalent. Diamond structure. The diamond structure is identical to the ZNS structure, except that both lattices are occupied by the same kind of atoms. For diamond, these atoms are C in case of the elemental semiconductors Si or Ge. Crystals are regular shaped solid particles with flat shiny faces. It was first noted by Robert Hooke in 1664 that the regularity of their external appearance is a reflection of a high degree of internal order. Crystals of the same substance, however, vary in shape considerably. Steno observed in 1671 that this was not because their internal structure varies, but because some phases develop more than others do. The angle between similar phases on different crystals of the same substance is always identical. The constancy of the interfacial angles reflects the internal order within the crystal. Each crystal is derived from a basic building block that continuously repeats in all directions in a perfectly regular way. This building block is known as a unit cell. One-dimensional lattices. The regular pattern of wagons can be described by placing a lattice point at the same place in each wagon. The arrangement of dots is the lattice, which has a given repeat distance. The motif is the wagon. The pattern is recovered by stamping the motif on each lattice point. Two-dimensional patterns. Planar lattices. Place lattice points at equivalent position in the pattern. Find smallest repeat unit that by translation can cover all space. All of these patterns have the same planar, lattice, square, but each has a different motif. The unit cells for the two-dimensional lattices are parallelograms with their corners at equivalent position in the array, that is, the corners of a unit cells are lattice points. Three-dimensional space lattices. The unit cell of a three-dimensional lattice is a parallel pipe defined by 3 distances A, B and C and 3 angles alpha, beta and gamma as shown in figure 1.3. Because the unit cells are the basic building blocks of the crystal, they must be space-filling. These are known as the 7 crystal system or classes. These unit cell shapes are determined by minimum symmetry requirement. Crystal structure repeat in 3 dimensions. Although there are only 7 crystal systems or shapes, there are 14 different crystal lattices called Bravais lattices, 3 different cubic types, 2 different tetragonal types, 4 different orthorhombic types, 2 different monoclinic types, 1 rhombohedral, 1 hexagonal, 1 triclinic. When these 4 types of lattice are combined with the 7 possible unit cell shapes, 14 permeable Bravais lattices are produced. It is not possible to combine some of the shapes and lattice types and retain the symmetry requirements. The 7 crystal systems are shown in the table. For an ionic crystal of known structure, it should be a simple matter to calculate the energy released on the bringing together the ions to form the crystal using the equation of simple electrostatic. The energy of an ion pair M plus X minus separated by distant r is given by Coulomb's law, and where the magnitudes of the charges on the ions are Z plus and Z minus with the cations and anion respectively. The energy due to Coulombic interaction in a crystal is calculated for a particular structure by summing all the ion pair interaction, thus producing an infinite series. The series will include terms due to the attraction of the opposite charges on cation and anions, and repulsion terms due to cation or cation and anion interactions. Figure depicts some of these interactions for the NaCl structure. The Na plus ion in the center is immediately surrounded by 6 Cl minus ions at a distance of r, then by 12 cation at a distance of 2 square root r, then by 8 anions at 3 square root r, followed by a further 6 cation at 2r, and so on. The Coulombic energy of interaction is given by the summation of all these interactions is given as equation 7. The term inside the bracket is known as the Madelung constant A, in this case for the NaCl structure. The series is slow to converge, but values of the Madelung constant have been computed not only for NaCl but also for most of the simple ionic structures. For 1 mole of NaCl, we can write the equation as equation 8. Now let us study how solids form bands and show their properties. When a group of atoms with similar energy combine, their molecular orbitals begin to form a band. A band contains molecular orbitals with only small energy differences between them, allowing the system to behave as a whole rather than individuals. These theories can help categorize the differences between insulators and metallic substances. The interaction of atoms with the same atomic orbital energies will create a system composed of molecular orbitals that can share electrons within the band. A more direct model for band theory says that bands are also formed by high energy orbitals in the system. These unoccupied orbitals can vary in energy differences or in some cases can be overlapping. These models help us understand the relationship between lower bands and higher bands. An insulator contains a fully occupied lower band separated by a large energy gap. A metallic material can have a partially occupied band or a fully occupied band overlap by a vacant band. Now in the end, let us summarize what we have learned in this lecture. A solid is defined as that form of matter which possesses rigidity and due to which possesses a definite volume and a definite shape. The solids can be classified into amorphous solid, crystalline solid. Classification of solid based on different binding forces: ionic solid, metallic solid, covalent network solids, and molecular solid. The crystalline state: infinite array of components. Strength of interaction is called lattice energy. Ionic and covalent crystal have similar lattice energies followed by metallic bonding. For an ionic crystal of known structure, it should be a simple matter to calculate the energy released on bringing together the ions to form the crystal using the equation of simple electrostatics.